Hello everyone. Today our group will be presenting on drum brakes, a key component in braking systems that's been used for decades in various types of vehicles. My name is Malinda Pereira and I'm joined by my teammates Joseph Espinel and Tobias Rikis. Together we will talk you through how drum brakes work, their components, advantages, disadvantages and their relevance in modern vehicles. To start off, let's talk about what drum brakes are. Drum brakes are a type of braking systems where brake shoes press outward against a rotating drum that's connected to a wheel. The friction between the shoes and the drum is what slows down or stops the vehicle. This design was invented by Louis Renault in the early 1900s, and it made its first appearance in 1902 on a car built by Wilhelm Maybach for Mercedes. Despite being over a century old, drum brakes are still used today, especially in rear wheels of some modern vehicles due to their simplicity and cost effectiveness. Now that we've seen the overall layout of a drum brake, let's break it down further and take a closer look at each individual component and its function. Now let's dive into two of the most important components inside the drum brake, the primary and secondary brake shoes. These shoes are curved metal pieces lined with friction material. They sit inside the brake drum and are responsible for actually making contact with the drum surface to slow down the vehicle. But they don't both work the same way. They have different roles. The primary shoe is one positioned toward the front of the vehicle. When you press the brake pedal, hydraulic pressure is sent to the wheel cylinder, which pushes the primary shoe outward first. It's the first point of contact with the drum and begins the brake process by creating initial friction. But the primary shoe doesn't work alone. As it presses against the drum, it also transfers some of the braking force to the secondary shoe through a connecting strut. The secondary shoe, which is located toward the rear of the vehicle, follows up by applying more pressure to the drum. Because of how it's positioned in relation to the rotation of the drum, the secondary shoe actually contributes more braking force than the primary. This happens because something called the self-energizing effect. As the drum rotates, it helps pull the secondary shoe even tighter against itself. That extra force boosts braking efficiency, meaning better stopping power with less effort. So in summary, while both shoes are essential, the secondary shoe does most of the heavy lifting, especially in terms of stopping power. Moving on, let's take a closer look at two more important components, the strut and the adjustment assembly, also known as the self-adjuster. Starting with the strut, this is a solid metal bar that connects the top ends of the primary and secondary shoes. It plays a key role in the braking process by helping to transfer force. When the primary shoe moves outward and connects the drum, the strut helps transfer some of the force directly to the secondary shoe, pushing it into the drums as well. But the strut doesn't just help during regular braking, it also interacts with the parking brake lever, allowing both shoes to press outward when the handbrake is applied. This ensures the vehicle stays securely in place even when the main hydraulic system isn't active. Now, let's talk about the adjustment assembly, a very useful part that often goes unnoticed. Over time, the friction material on the brake shoes wears down. As that happens, the gap between the shoe and the drum increases, which can make braking less responsive. The self-adjuster mechanism helps solve this. It works by gradually expanding the shoe outward as the lining wears out, making sure that stay properly positioned closer to the drum. Most self-adjusters are mechanically activated when the vehicle is moving in reverse and the brakes are applied. So even though you might not notice, the system is quietly making sure your brakes stay effective and responsive over time. Next, let's talk about the anchor pin. This part acts as a kind of pivot or stopping point for the brake shoes. It is usually located at the top of the backing plate where the primary and secondary shoes meet. When the brake shoes are forced outward against the drum, the anchor pin is what holds them in place and absorbs the opposing force. Without the anchor pin, the shoes might actually move or rotate with the drum, which would make the braking action ineffective or unstable. So while it may look like a small part, it plays a very important role in maintaining the alignment and control of the shoes during braking. Now let's talk about the parking brake lever. This component is typically connected to the rear or secondary brake shoe and is linked to the handbrake or foot-operated parking brake inside the vehicle. When the parking brake is engaged, this lever manually pushes the brake shoe outward, pressing it against the drum, even when the hydraulic system isn't active. That means you can safely park on a hill or incline and trust that the wheels will stay locked, because the parking brake system holds the shoe in place mechanically, not hydraulically. This function is especially important as a backup system, ensuring the vehicle remains stationary even if the main braking system fails or is turned off. Finally, the last key part of the drum brake system is the parking brake cable. This cable is what connects the handbrake inside the car to the brake mechanism inside the drum. When the driver pulls the handbrake lever, the parking brake cable is tensioned, and that force is transferred directly to the parking brake lever we just talked about. What's important here is that the cable operates entirely mechanically. It doesn't rely on hydraulic pressure, so it works even if the main brake system fails or the engine is off. This is especially useful for keeping the vehicle securely in place when parked, and it also serves as a backup system in case of an emergency. So overall, the parking brake cable plays a crucial role, ensuring that the braking can still occur when you need it most, without any reliance on electronics or fluid pressure. Well, that wraps up the component breakdown from my side. Now I'll hand things over to Joseph, who will take you through the next part of our presentation. Thank you.
Drum brakes operate by converting a vehicle's kinetic energy into heat through friction. When the driver presses the brake pedal, hydraulic fluid from the master cylinder enters the wheel cylinder. This pushes the shoes outward until they press against the rotating drum, and the resulting friction slows the wheel down. Once the pedal is released, the springs retract the shoes so the wheel can rotate freely again. Drum brakes have this self-energizing effect where friction from the drum's rotation actually helps press the shoe even harder, therefore reducing the input force required from the driver. Drum brakes are commonly used in rear wheels of passenger cars since the front wheels carry most of the braking load. They are standard for parking and emergency brakes because of their strong holding ability. Heavier trucks and buses also use them because of durability and cost effectiveness. They also appear on motorcycles and bicycles, but they're usually at the rear where braking demand is lower.
The advantages of drum brakes are that they are cost effective, they can have an integrated parking brake, and they offer protection from the elements. As far as cost effectiveness goes, drum brakes are cheaper to produce than disc brakes. This makes them a more affordable option for vehicles, especially when they're located on the rear wheels. As for the integrated parking brake, the design of the drum brake makes it relatively easy to add a mechanical parking brake. The parking brake cable pushes the brake shoe and drums together, holding the wheel in place. This removes the need to have a separate caliper and rotor setup like with disc brakes. Finally, they offer protection from the elements. The whole braking mechanism is contained within the drum. This design helps to protect the brake shoes, springs, and wheel cylinders from dirt, splashing water, and road debris. Without this protection, the lifespan of the components would be significantly diminished. The disadvantages of drum brakes are that they have poor heat dissipation, they're mechanically complex, and that they're water sensitive. As far as heat dissipation goes, drum brakes don't dissipate heat as well as disc brakes. Under heavy braking, the drums heat up and expand. This expansion increases the distance between the brake shoe and the drum, causing the vehicle to experience brake fade. This is why they're not recommended for high performance or heavy duty vehicles. The next disadvantage is their complexity. Drum brakes have a more complex internal components than disc brakes. Drum brakes contain multiple springs, levers, and adjusters. This complexity makes them more difficult and time-consuming to service in comparison to disc brakes' relatively simple caliper and pad assembly. The final disadvantage is drum brakes' water sensitivity. While the enclosed design of the drum brakes helps to protect them from some elements, excessive water isn't one of them. If you were to drive through a deep puddle and get water inside of the drum, it can take them a while to dry. This can cause a temporary reduction in the braking effectiveness until the water dissipates.